Welcome to Visual Algebra Lecture 4.2, Embeddings and Quotients. In this lecture, we will explore two types of homomorphisms, those that are injective, called embeddings, and those that are surjective, or onto, called quotients. The kernel of a homomorphism is the set of elements that get mapped to the identity. This is the group-theoretic analogue of the null space of a matrix. We will show that the kernel is always a normal subgroup and that the cosets are the preimages of the individual elements in the image. This will motivate the so-called fundamental homomorphism theorem that comes next, that says that every quotient map can be achieved by applying our quotient process from chapter 3 to these cosets. Okay, let's get started. Consider the following homomorphism theta from Z3 to C6 defined as theta of n gets sent to r to the 2n. For example, 0 gets sent to r to the 0, 1 gets sent to r squared, and 2 gets sent to r to the 4th. This is an embedding. You can see how the subgroup lattice of the domain embeds into the subgroup lattice of the codomain. Also notice that because this first group is additive and the second group is multiplicative, that the homomorphism condition amounts to theta of a plus b equaling theta of a times theta of b. In terms of the Cayley graph, the red arrow representing the generator 1 gets mapped not to an arrow in this graph, but a two-step path, r squared. A homomorphism like this one, that is one-to-one or injective, is an embedding. I typically like one-to-one, but the nice thing about using the term injective is that I can use the noun form injection. In this case, the group G embeds into H as a subgroup. In other words, the image is isomorphic to the original group itself. We will prove this in the next lecture. We don't have to, but if we want to emphasize that a particular map is one-to-one, we can use this little curly arrow like this. If we don't use it, we can't say anything, but if you see something like this, you know it's one-to-one. If phi of G equals H, remember G is the domain and H is the codomain, then the homomorphism is onto or surjective. This has a nice noun form, which is a surjection. We call it a quotient. If we want to emphasize that a particular map is onto, we use this double arrowhead like that. Again, this is optional, so if you don't see it, you can't assume anything. A homomorphism that is both injective and surjective, in other words, it is bijective, is an isomorphism. An automorphism is an isomorphism from a group to itself. It's important to realize that even though we defined embeddings and quotients separately, many homomorphisms are neither. For example, consider the homomorphism phi from the quaternion group Q8 to the alternating group A4, defined by sending I to the permutation 1, 2 times 3, 4, and j to the permutation 1, 3 times 2, 4. I only need to define a homomorphism on the generators, and then I can use the defining property of homomorphisms to determine the image of the other elements. For example, phi of k equals phi of ij, which is phi of I times phi of j, which is 1, 2, 3, 4 times 1, 3, 2, 4. And that's just the third element of this form, 1, 4, 2, 3. Similarly, phi of negative 1 is phi of I squared, I times I, which is phi of I times phi of I, which is the square of this permutation, which is the identity. And I'll let you check that phi of negative g equals phi of g for I, j, and k. And again, this is just because phi of negative g is phi of g times phi of negative 1, and this is the identity. Here's that homomorphism in terms of Cayley graphs, and I want you to notice something. So first of all, x, y, and z are these elements up here, That's the same convention that we used when we saw these Cayley graphs in these groups in chapter 2, because I can't really fit these permutations in these nodes very well. But notice how when I'm circling, these are cosets of a particular, first of all, this subgroup gets mapped to the identity, and the cosets of that subgroup are the elements that get mapped to the other elements. So in other words, we are applying the quotient process to this group, and then we are including that into a larger group, A4. So that's going to be a theme, and that is not a coincidence. Let's do another example of a homomorphism, this time of an isomorphism. We have already seen that D3 is isomorphic to S3. Formally, this means that there is a bijective correspondence between the elements, but not just any bijection will do. Intuitively, the permutations 1, 2, 3 and 1, 3, 2, as 3 cycles, they should be rotations. Think of a triangle now. The 2 cycles, 1, 2, 1, 3, and 2, 3 should be reflections, and then the identity permutation must be the identity symmetry. It is easy to verify that the following map is an isomorphism. So phi goes from D3 to S3, and it sends R to the permutation 1, 2, 3. If you label a triangle like this, you can think of R as just being the rotation. So it sends 1 to 2, 2 to 3, 3 to 1. So there's that permutation. And F is the permutation that flips the corners 2 and 3. So that's about this axis. The corner 1 is fixed. So here's Cayley graphs of these two groups. And notice that, again, there's a bijective correspondence here. And also, once I fixed what a rotation was and what a horizontal or a flip was, let's just say a flip, then that determines what everything else is. For example, if I write that, let's see, 1, 2, 3 times 2, 3 is 1 goes to 2, 2 goes to 3, 3 goes to 1, and then 2 is fixed. So that just means phi of R times phi of F equals 1, 3, and this is phi of RF. So in other words, RF is this reflection here, and we can know that just from using the homomorphism property. I should emphasize that this is not the only isomorphism between these groups. I could just as easily send R to 1, 3, 2 and F to any of these reflections, and it would have worked. Another place where homomorphisms arise are representations. We have already seen how to represent groups as collections of matrices back in chapter 2. Formally, a faithful representation of a group G is a one-to-one or injective homomorphism from G into a group of matrices over some field K. Think of K as like the real numbers, the complex numbers, or ZP, though it could be some other field. In the branch of mathematics called representation theory, representations do not need to be one-to-one or maps or embeddings. However, in this class, when we speak about representations of groups, we are typically thinking about a case when there is a subgroup of G sitting inside of a group of matrices. So the individual elements really are represented by matrices. So that happens when phi is an embedding and the representation is faithful. But if I don't use this word, unless I say otherwise, I will typically be assuming that representations are faithful. Here's an example that we saw in chapter 2. The following 8 matrices form a group under multiplication isomorphic to Q8. Formally, we have an embedding from Q8 to GL4R. This is the set of invertible 4x4 matrices with real coefficients. And there's many ways that we could define this map. So here I just picked one. I said, let's let this matrix be I, and this matrix be J, and this matrix be K. That just means that phi of I is this matrix, phi of J is this matrix, and then phi of K is going to have to be, by the homomorphism property, phi of I times phi of J, and that forces it to be this one. But many other maps could work. We could have let I be the negative of this matrix and J be this matrix. And then I times J is going to be whichever one of these two matrices is the product. And that would be phi of K. Let's now turn our attention to quotient maps, which are homomorphisms that are onto. I hinted at the beginning how these arise from our quotient process. But to formalize that, we need the concept of a kernel of a homomorphism. This is going to come up throughout the course. That's just the set of elements in the domain that is mapped to the identity element in the codomain. This is the group-theoretic analog of the null space of a matrix. Remember, that is the matrices that get mapped to 0. You may have noticed that I snuck in this notation right here, and let me explain what that means. If phi is a homomorphism from G to H, and we have an element, little h, in the image, then we can define the preimage of H to be the set of elements in the domain that get mapped to it. So the kernel can be thought of as just as the preimage of the identity element in the codomain. I want to emphasize, and this is important, that this notation that we are using is in no way suggesting that phi inverse is a function. In other words, generally, a homomorphism need not be invertible, but we can always define the preimage using this notation. In general, this is not going to be a function unless phi is 1-to-1, and even then, the domain will not necessarily be all of H unless phi is bijective. Let's do some examples and observe what the kernels and preimages are. Recall that the cyclic group Cn, written multiplicatively, is just the nth roots of unity. So C2 is the second root of unity, which is 1 and -1. Consider the following quotient map. Phi goes from D4 to C2, and I'm going to define it on the generators as follows. Phi of R is 1, and phi of F is -1. So you can think of this as saying +1 means orientation preserving, as rotations are, and -1 means orientation reversing, as reflections are. Indeed, using our homomorphism property, it's straightforward to check that phi of any rotation is just 1, and phi of any rotation, r to the kf, is going to be phi of r to the k, 1, times phi of f, which is -1, so that's -1. Here is a Cayley table of D4, and here I have overlaid the image of each element. So if you squint your eyes, you can see the structure of the group C2. So this says if you take any rotation times any rotation, you get a rotation. Take any rotation times any reflection, you get a reflection. And a reflection times a reflection is a rotation, and so forth. Notice that the kernel of this map, which is the preimage of the identity, is the subgroup of rotations. That's the subgroup generated by R. And the preimage of -1 is the 4 reflections. This is the other coset of this subgroup. This is going to be something that is going to hold for all homomorphisms, namely that the preimages are going to be cosets of the kernel. Let's see another example, a familiar one, again, now that we have some more terminology. Define the homomorphism phi from the quaternion group Q8 to the Klein 4 group V4 by sending I to V and j to h. Recall that we saw this in Chapter 3 when we introduced the quotient process. Since Q8 is generated by I and j, we can determine where phi sends the remaining elements. So phi sends the identity to the identity. You see why that is? Well, phi of 1 is phi of I to the fourth, which is phi of I to the fourth, which is v to the fourth, which is the identity. Similarly, -1 gets sent to the identity. K gets sent to phi of I times phi of j, which is r, that's the rotation, the 180 rotation. And then the negative ij's and k's get sent to the same element as ij and k. We saw this earlier in this lecture as well. Notice that the kernel of this homomorphism, which is the preimage of the identity, is just a subgroup containing 1 and -1. So this is phi, the preimage, I don't want to say phi inverse, it's phi -1 of E. And then the other cosets, so these are the two elements that get mapped to V. So phi -1 of V. These are the two elements that get mapped to H. And these are the two elements that get mapped to R. So an example that this holds here is not a proof that it holds in general, but it hopefully should give you some important intuition. Let's finish this lecture by proving two of the statements that I have claimed and we've seen by example. First of all, that the kernel of any homomorphism is a normal subgroup. So let's denote the kernel by n. The first thing we have to do is show that it actually is a subgroup. So let's take any two elements a and b in n, and we got to show three things. First of all, the identity. So we proved in the previous lecture that for any homomorphism, the identity in G gets sent to the identity in H. I'm going to write these both without subscripts because I think it should be clear from the context. What about closure? So phi of A times B. So we're taking two elements here in n, meaning that they get mapped to the identity, and we want to show that their product gets mapped to the identity. So phi of AB is phi of A times phi of B. If you don't know where to go, sometimes you just, helps to just, when you see phi of AB, it's almost like a knee-jerk reaction. Split them up like this. And both of these are the identity element because that's the definition of the kernel. And so that is the identity. So indeed, two things in the kernel, their product gets mapped to the identity as well. And finally, let's do inverses. So what we have to show is that if we have some element in the kernel A, then its inverse is in the kernel. So phi of A inverse is phi of A inverse. We showed that in the previous lecture, which is E inverse, which is equal to E. So therefore, the kernel is a subgroup. Now, you may remember that there's something called the one-step subgroup test that we could have used instead. And so for that one, if we take two elements in the kernel, we have to show that AB inverse is in the kernel as well. And that's actually, it is shorter. So I could have done phi of A B inverse, which is phi of A phi of B inverse, which is E times E inverse, which is the identity. And it would have saved a little bit of work here. Okay, now let's show that the kernel is normal. So let's write, show that the kernel is normal. So remember, there's three ways to do this. We can show that every left coset is a right coset, or we can show that if we conjugate this, we get itself. But the one that is typically easier is to show that this is closed under conjugation. So let's take any element little n in the kernel And we will show that if we conjugate by it, G inverse, we remain in the kernel for all elements in the group. And this kind of falls in our lap. So let's see. First of all, what does it mean for this to remain in the kernel? Well, that means that it gets mapped to the identity by definition. So phi of G inverse equals phi of G, phi of N, phi of G inverse, and this is phi of G. We don't know what that is, but since N is in the kernel, this is the identity, and then this is phi of G inverse. So these things are inverses of each other, so they cancel, and indeed we get the identity. So that's what we had to show. We took an element in the kernel, we conjugated it, and it still got mapped to the identity. So therefore, N is normal. At this point, I want to make a key observation. And that is, given any homomorphism phi from G to H, we can always define the quotient group G mod the kernel of phi. As we've seen, the image of a homomorphism is what we get by taking the quotient by the kernel, and that is going to be a general theme. So not only can we always define the quotient G mod the kernel, but every homomorphic image is going to have that form. So this basically describes all homomorphisms. That is the first of typically 4 central theorems in group theory called the isomorphism theorems, and we will call it the fundamental homomorphism theorem, and we will devote the next lecture just to that. But before we can get there, we need to prove one more fundamental result, something that we've already talked about and have seen examples of. That is, if we have a homomorphism, phi, from G to H, then the preimages of the other elements are the other cosets of the kernel. So let's prove this. And as before, we will let N be the kernel of phi. And let's now take any element in the preimage of H. So let's take any G in phi negative 1 of H. Notice I'm not saying phi inverse because it's not an inverse map. What this means is that phi of G equals H. So what are we trying to show? We want to show that the preimage of H is an entire coset of the kernel. So in other words, well, if that's true, then we can use any representative or any element in that set as a representative. So let's just use G, and we can write Gn. So this is what we're trying to show. And to do this, we need both containments. We need to establish both of these. Okay, so how do we do this? Maybe it's not clear, so let's try one containment, and let's take an element in the left-hand side and show that it is in the right-hand side. So we'll take an element, let's call it A, in phi inverse, sorry, I said it again, the preimage, phi negative 1 of H. And what it really means is that phi of A equals H. We need to show that it's in the right-hand side. So we need that A is in Gn. In other words, A is just G times some element in the kernel. So how do we do that? Well, this condition here, let's unpack that a little bit. So being in this coset, as we've seen, is the same thing as saying an equals gn. That's one of the basic properties of cosets that we've proven. And then we can write, we can move the g over and write this is the same thing as g inverse a, n equaling n. And by our boring but useful coset lemma, I still don't have a better name. Remember, that's xh equals x if and only if x is in h. This is equivalent to saying that g inverse a is in n, which is the kernel of phi. So in other words, phi sends g inverse a to the identity. Okay, so we're trying to show this thing that let me put circled and put a star there. And we really just have to show any of these equivalent conditions. But I claim that this last one, something that we could check. So why is that true? Well, phi of g inverse a, what is that? That's phi of g inverse times phi of a. And what are g and a? G is in the preimage of h. G gets mapped to h, and also a gets mapped to h as well. So this is just h inverse times h, which is the identity. And so yes, indeed, this condition is true. That's equivalent to what we wanted to show. So that confirms the first containment. And now let's do the second containment. So we have to pick some element in the right-hand side and show that it's in the left-hand side. In other words, that gets mapped to h. And that's basically just running this argument in reverse. If you don't quite see it, let's check it. So let's take any element g little n in the coset g big N. And again, we're trying to show that this element gets mapped to h. It's in the preimage. Well, then phi of gn is phi of g, phi of n, which is, what's phi of g? That's h. What's phi of n? That's the identity, because that's in the kernel. And that's equal to h. And that's exactly what we wanted to show. So that finishes the proof. And now we are all ready for the fundamental homomorphism theorem, which is coming up next. And remember, that just says that every homomorphic image is a quotient. And that will open the doors to the other isomorphism theorems, which, well, if we know every homomorphic image is a quotient, what are the next things we should ask? How about let's understand the structure of a quotient. What are its subgroups? Which ones are normal? What happens when you take the quotient by one of those normal subgroups? And things like that. So that's coming up in the next couple of lectures. Stay with us.